Hey everyone, welcome back to Everything is Relative with me, Mr. K. Today we're going to be doing a crash course on the topic of quantum physics for Cambridge A-Level Physics. Now, many of you may be familiar with the idea of quantum mechanics, or you would have heard the phrase somewhere. Quantum physics at the A-level is going to give us an important base or important foundation to understand quantum mechanics if we want to study physics later on. Now, the word quantum simply means an amount of something. And so we'll see how that relates to the amount of energy that objects can have on the quantum scale. So before we get into that, let's start with the basics. Let's talk about photons. Now we all have some idea of what a photon is, roughly. And photons can be thought of as, well, things that carry light, a particle that's responsible for carrying light energy. So if I were to draw a representation of what a photon would look like, if I represent a photon by a wave, it travels with speed c, and this speed is the speed of electromagnetic radiation. Light is an electromagnetic wave. So what is a photon? It is simply a wave that carries electromagnetic radiation, whatever that means. So when we studied Young's double-slit experiment, we showed that light behaves as a wave. It undergoes diffraction and interference. And so this wave, we're going to introduce a new quantity. The energy that this wave carries, that a single photon of light carries, is hf, where h is called Planck's constant, after the German scientist Max Planck. And this number is a tiny number. Again, quantum physics deals with the small scale, on the subatomic scales, and particles that are tiny enough so that the laws that we learn from Newton break down. And so we deal with really small objects and really small numbers. From our knowledge of waves, hf is simply hc over lambda. From the wave equation, c is equal to f lambda. The value of h, the value of Planck's constant, is tiny. And all of this falls into the past 150 years or so. This is why we call this modern physics. It's relatively modern on the scale of science. So it's 6.63 times 10 to the minus 34. And the units of measurement for this are the joule second. So Planck's constant is a tiny number, almost negligible. So how can I represent a photon in a different way? Well, it turns out that a photon carries a fixed amount of energy, which we can see from that equation, E is equal to hf. And so I can draw, or I can visualize a photon as a packet that has a wave in it. And again, this is just a representation. This is not a physical thing. This is what we can assume a photon looks like if you're trying to picture it. So it contains a specific amount of energy, which we'll call a quantum. And this amount of energy is fixed. It can't contain any more or any less than that amount of energy. And this energy is in the form of electromagnetic radiation. Now, the reason why I say that this is a packet of energy is because the energy that is contained in this photon is constant. It cannot change and it cannot vary continuously. We are used to energy varying continuously when we heat water, for example, where the amount of joules that the water can have as it heats can be can take any range of infinite values. But this packet only has energy hf, and if I have two of these packets, then I have 2hf. And so I can only have multiples of hf for these kinds of photons. So the first thing you may notice when you look at your textbook is that we define, and I'm not going to show you why this is so, you're just going to have to trust me, the momentum of a photon is E upon c. Yes, photons have momentum even though they have no mass. And so the equation is not simply mv like it is for a massive object. And if I take the equation from above, HF as my energy, I get P is HF over C, which I can write as, I remove the F and replace it with the wavelength of this photon, hc over lambda c, and this simplifies to h upon lambda. H again is Planck's constant. And if you look at the units, you can figure out that yes, the units are the units for momentum. Now, the units that we're going to use, and I represent the units of measurement with a square bracket for energy, is going to be the electron volt. So we're going to move away from the joule. And if you recall that 1 electron volt is equivalent to 1.6 times 10 to the minus 19 joules. Because we're working with small objects, photons are tiny particles, they have tiny energies. So it becomes more convenient to work with the electron volt rather than the joule. And obviously, from our prefixes, we know that 1 mega electron volt is 10 to the power 6 electron volts. Many of our measurements in quantum physics are on the order of mega electron volts. And so that just for revision, to remind you what a mega electron volt would be. So let's move on to something that Einstein discovered and later won the Nobel Prize for, the photoelectric effect. Everything I've told you thus far has shown or has taken the idea from Young's double slit experiment that light is a wave. Okay. What did Einstein do? Well, as you may know, and we can recall, Einstein had light incident onto certain metals, onto different metals, and what he found was quite intriguing. So I take a metal surface, and I take a high frequency, high energy. I'm going to represent it with the blue, with the color blue. A blue photon strikes, or something with a higher frequency and hence higher energy than blue, strikes this metal, and what do you know? An electron is ejected. And this later became known as photoelectric emission. It's the basis upon which our solar panels work currently. Light strikes a metal, out comes an electron. If multiple photons of light were to strike this metal, more electrons would be emitted so that we could actually create a current and hence we could generate electricity. But what was really interesting was when you take the exact same metal and you lower the frequency and hence lower the energy of the incident light. So let's say we have something red or lower than red, infrared, etc. The energy HF2 of this photon, the photon strikes the metal and no electron is emitted. And you could incident this metal, you could strike this metal with this red photon all day long, as many as you wanted, and still no electrons would be emitted. This was very strange. And Einstein said this could only happen if light is behaving as a particle and not as a wave. Because if light were behaving as a wave, then after supplying the metal with enough red photons, electrons should be emitted. But it was only at a certain specific frequency at which electrons were emitted. Higher frequencies emitted electrons, lower frequencies did not. And that frequency was called the threshold frequency, which we'll come to soon. But what we can see is that F1 is greater than F2, and so he noticed that the frequency determines the emission. And in this case, the frequency also was represented by a different color. Okay, but sometimes, for most metals, we need frequencies much higher than blue light, ultraviolet, gamma rays, etc. What he also noticed was that the electrons were emitted instantaneously. I'm going to try and spell this correct. Instantaneous emission was another nail in the coffin of the idea of light being purely a wave. And so if light were a wave, there would have to be some energy transference from the photon to the metal to the electron before the electron was ejected. But the emission was instantaneous, and so this showed that light could not be a wave. The photon struck the metal, disappeared, and out came an electron. What we currently say is that the minimum frequency for which emission is possible is called the threshold frequency. So we label the threshold frequency of a metal by F subscript 0, F naught, and hence the maximum wavelength, since frequency and wavelength are inversely proportional, the maximum wavelength, which in this case, in our example, we can assume to be blue, the maximum wavelength of the light that will emit a photon is called the threshold wavelength. This is just terminology. And I guess you would represent the threshold wavelength by lambda naught. If we increase the intensity, if I increase the number of photons, number of blue photons in our case, if I increase the number of blue photons striking the metal per unit time, what I get is a higher rate of emissions. So electrons will be emitted at a much higher rate. So if I increase the rate at which the photons strike the metal, then I increase the rate at which the electrons are emitted. And this tells me that every photon is emitting an electron. So there are many observations here that are putting to bed the idea that light is purely a wave. And the minimum energy that's required. So the minimum frequency will be associated with the minimum energy. Remember, E is equal to HF. For the threshold frequency, we get a value of E, and we call this minimum energy the work function energy of that metal. And different metals have different work function energies, with sodium being one of the lowest, so being one of the best metals to be able to test out for yourself how this photoelectric effect occurs. And so what Einstein effectively did was show that photons are actually particles, and each particle has a specific value of energy, HF. And so if I had two photons, I would have an energy 2HF, and I could not have an energy in between. So hence the word quantum. The word quantum is arising again. So if we were to summarize the effects here using the conservation of energy, again, you can do this, you can derive these equations in your spare time, but in comes a photon of light, a single particle now, striking some metal and ejecting a photon in the process. The work function of this metal is phi. That's the minimum amount of energy that needs to be given to the metal before an electron is released. And we'll assume that this photon does have that energy, and it has a little bit more. Then what happens? An electron is ejected, and when the electron leaves the surface of the metal, it gains some kinetic energy. A half me we'll use as the mass of the electron, V max squared, so whatever that maximum speed may be. And so using the conservation of energy, we can say that the incoming photon deposits energy to the metal, has to overcome the work function, gives some of the energy to the metal. Once the work function is overcome, the electron can be released from the surface of the metal and gains kinetic energy a half mv squared. And so this is the photoelectric equation. And remember, the work function can be written as the minimum amount of energy that needs to be given to the metal for an electron to be sitting at the surface without any kinetic energy, HF naught, plus a half mv squared. And so this is the photoelectric equation. And you'll use this equation to calculate various quantities given a specific example of the photoelectric effect occurring. Again, don't forget the work function is h times the threshold frequency f0. And so here we have an equation that describes in totality what's happening in the photoelectric effect. And you can easily derive this equation for yourself by drawing a simple diagram and thinking where's the energy coming from and where's it going. So obviously this leads us to the idea, well, I showed that light, well, not me personally, but Thomas Young showed that light behaves as a wave. But here, Einstein showed that light behaves as a particle. And so what we have is something called wave-particle duality. And if it exists for photons, well, surely it exists for other particles as well. And Louis de Broglie showed, before any experiments were done, he proposed that all particles actually have an associated wavelength, given by the equation that we derived earlier, h over p, which for everyday massive objects, things larger than your subatomic particles, would be h over mv, anything other than a photon, that is. And this became known as the de Broglie wavelength. And this hypothesis of his was proven a few years later when it was shown that electrons can actually undergo diffraction. And that sounds weird. Electrons are particles. They are physical things that take up space. And for them to undergo diffraction means that they can exist in more than one place at any given time. And so they must be waves as well. And so what was shown from that experiment that was carried out a few years after was that electrons have wave-like properties. And so it should be said that all particles can have wave-like properties. But again, these ideas we usually apply to the very small. Remember, quantum physics is the physics of the very small, the small-scale study of the universe. So showing that electrons diffract, it was shown that electrons have wave-like properties. And so the wavelength of tiny particles moving with speed v, having mass m, is h over mv. So yes, electrons can move with the speed v, and they have an associated wavelength. So they actually occupy a region in space rather than just a position in space, which is strange if we think about all of the physics that we learned thus far, where we always treated these things as particles. And so we have to now talk about what happens inside an atom that prevents us from, if we go back to what we spoke about earlier, prevents us from having continuous amounts of energy. Rather, our energy is always discrete. It's discrete for photons, and we've shown that it's actually discrete in atoms as well. So I'm just going to do a basic example. Imagine we have a prism. It could be a perspex prism, a glass prism, it doesn't really matter. And I'm going to use gray, but it's going to represent white light. So I take white light and I shine this on a prism. Now, most of you probably already know what will happen as the light passes through the prism. The light diffracts, and we have light of varying colors appearing at the other end. In this case, we'll draw it with the right colors. We'll have red at the top, refracting the least, and we'll have violet with a greater amount of deviation. And again, this is any prism. And so this dispersion of light is what we call the emission spectrum of white light. And so that means white light, after undergoing dispersion, produces a spectrum of all the colors of visible light, and some of the higher and lower orders that we can't see. But this is very much a continuous spectrum. I see all the colors, I see no gaps in between. And so we call this a continuous spectrum. However, if I want to observe the emission line for hydrogen gas, that is, if an electric current is passed through a glass tube that has hydrogen gas at a low pressure, we notice something strange occurring. We notice that the spectrum that is produced is not a continuous spectrum with all the colors of the rainbow. In fact, what we have is, don't have all the colors, but we have a violet line. We have one that is slightly more purple. Close together, a little further away, we have a blue line. And so if the light from the hydrogen lamp is passed through a prism and we are allowed to observe the dispersion pattern, what we find is very different from that of the prism. Instead of getting the entire rainbow, what we get is something like this. And we call this the emission line spectrum. And very specifically, this is for hydrogen gas. So this is the emission line spectrum of hydrogen. And if I use different gases, if I were to use a mercury lamp, etc., I would get different patterns, different emission lines. And this shows that I don't have a continuous spectrum occurring. These lines are very distinct. They are discrete. There's 4 of them. If I just consider these 4, there are only 4 of them. And this is clearly not continuous. Using a different gas, I could have more or less lines, but I will still have a discrete number of lines. I won't have an entire spectrum showing. So what does this tell us? This tells us that the electrons in atoms for a particular element have very specific energies, because photons are being emitted, but photons are only being emitted, in this case, in 4 different wavelengths: violet, purple, blue, and red. So they can't have a continuous energy, because if they did, they would be emitted with all the colors of the rainbow. So importantly, what we learn from this is that the electron energies inside the atom are also quantized. Why do I say the electrons specifically? Because remember, electrons, when they are accelerated, they release photons of light. You may remember this from IGCSE. And so the electrons that are contained in the atoms of hydrogen are the ones that are gaining the energy, but are only gaining the energy in specific amounts. So the electron energies in atoms are quantized. So what does this mean? So it turns out, if I were to think of an atom with a nucleus in the center, and then my electron orbiting the nucleus, so I have neutrons and protons, positively charged nucleus with a negatively charged electron. This electron can exist, as you know, in different orbitals around the atom. And we say that the energy gets higher as the electron goes to the outer orbitals. So if we take this picture and linearize it for convenience sake, we say that the closest orbital, or the one that's closest to the nucleus, has the lowest energy, and we call this the ground state. And then we can include our other energy levels, and this is very specifically for the hydrogen atom, but it takes a very specific shape. So we draw what we call an energy level diagram, very basic energy level diagram, and these are very clearly discrete. So these are discrete energy levels for hydrogen. The lowest energy, referred to as the ground state, in the case of hydrogen is minus 13.6 electron volts. We use negative here just for convenience. So negative 13.6 electron volts means if I want to completely remove the electron from the hydrogen atom, I need to supply 13.6 electron volts in order to get it to just leave the atom of hydrogen. That's also known as the ionization energy. And the next is minus 3.4 electron volts, minus 1.5 electron volts, and minus 0.85. We haven't included all the energy levels. I'm just going to consider the first four. But the higher energy states are known as excited states. So what's actually happening? How am I getting these specific lines coming from hydrogen gas rather than a complete white spectrum? So what I'm going to do is I'm going to consider, let's maybe do this a little bit more geometrically. I'm going to consider the first three energy levels for convenience sake. And I'm going to take an example. So let's consider three energy levels. Let me label these energy levels as minus 13.6 eV, minus 3.4 eV, and minus 1.5 eV. Again, this is just an example. The electron in my atom is sitting at the lowest energy level. It's sitting at the ground state. And so here's my electron with its lowest possible energy, with its most stable configuration at the ground state. And so I have, as an example, I'll just copy this picture across. And so I'll just move this so we have more space. And so I have three scenarios. So here I have an electron sitting at the ground state, and in comes a photon. Let's assume it's a photon of low energy. It doesn't necessarily need to be a red photon, it's just a photon with low energy. And its energy is HF. Now the electron can only absorb the energy HF if HF is equal to the difference between any two energy levels, because the electron cannot exist in between levels. The electron must have a discrete amount of energy. So the electron absorbs the energy and is moved to the higher energy level. So it now has a greater energy and is moved to the higher energy level. It has absorbed the photon and increased its energy. It's more excited than it was before. The only way the electron can lose that energy is by giving it out somewhere. And guess what? It gives it out in the form of a photon. So for the electron to lose its energy, for you to lose energy after you've drunk some coffee, is to play sport or to dance or some sort of exercise to burn out the coffee that you've had. Similarly, the electron must have a way of giving off this energy, and so it makes a transition from high energy to low energy, and in the process it gives off an identical photon to the one that excited it in the first place. And the photon has exactly the same energy HF. So by the conservation of energy, energy is neither created nor destroyed. It is given from the photon to the electron to increase its energy level. When the electron transits back down to the ground state, it gives off a photon of exactly the same wavelength, exactly the same frequency. If I change the energy to something that's a bit higher, So something with a much higher frequency and a much lower wavelength. Blue, I'll use a blue pen to represent it in this case. It doesn't need to be blue. It could be anything blue or higher even. So in comes a photon, energy HF, and if the energy of the incoming photon is equal to the difference between any two energy levels for that atom, the electron will accept that photon, absorb that photon's energy, and then make the transition to a higher energy level, in this case to the second excited state. So it has gained more energy and hence is sitting at a higher energy level. Again, in order for the electron to move back to the ground state, it must give off the energy in some way, and again this energy will be given off in the form of exactly the same photon that excited it in the first place. And so the electron transition now happens from a higher energy level back to the ground state, and so obviously the photon being emitted is of a higher energy than the initial one that excited it. So let's summarize what has been happening in this process. So initially, the incoming photon has energy HF. We'll consider the red photon for now, and that energy is equal to the difference between the first two energy levels, the ground state and the first excited state, delta E. And that is the final energy minus 3.4 electron volts minus the initial energy minus 13.6 electron volts. And so the change in energy was 10.2 electron volts. So that means the photon that was incoming had an energy of 10.2 electron volts, which is the same as the difference between the first two energy levels. We then say that the electron was excited. The electron is excited to a high energy level, but the atom becomes unstable. Or the electron now needs to give off the energy in order for the atom to reach its ground state again, its more stable configuration. And in order to do so, the electron needs to jump back to the ground state and release a photon of energy HF, which again must be equal to the difference between energy levels, delta E, which in this case is minus 13.6 electron volts minus 3.4 electron volts. That's simply plus 3.4 electron volts, which will give me minus 10.2 electron volts. So in this case, the atom is losing energy in the form of radiation, hence the change in energy is a negative. And the photon that leaves also has an energy of 10.2 electron volts, meaning it is identical to the one that excited the electron in the first place, or excited the atom. And so we can see that these are only for the first two transitions, which I've shown as red and blue. And if we go up to our hydrogen atom, that's where our red line and blue line come from. If I drew more energy levels for the hydrogen atom, the ones that are emitted, I would see that the transitions would give me purple and then violet light. Those would be the photons that were emitted, and hence the photons that could excite the atoms in the first place. So that's why we say that energy levels in an atom are discrete and not continuous. So what we can see from this is that HF, or Hc over lambda, must be equal to the difference between energy levels, delta E. That means the wavelength of the photon that is emitted, and hence the color of the photon that's emitted, can be determined as Hc over delta E. And so I can tell the wavelength that's required to excite an electron, and also that will be emitted when an electron is de-excited, using this equation. H, which is the Planck's constant, C, which is 3 times 10 to the power 8, which is the speed of electromagnetic radiation, divided by the difference between energy levels. So purely all I really need is the difference between energy levels of a specific atom to tell the wavelength of light that will be emitted when the electron in that atom is excited. So lastly, after having spoken about the continuous spectra, let's talk about the absorption spectrum. So what is an absorption spectrum? So if I pass white light through a low pressure gas, something happens. And again, this will be in your textbook, and you can do extra research, you can read up about where this applies, but we're going to use the idea of astronomy and cosmology for now. In many stars, we have a low pressure gas on the outside of the star, and most stars emit radiation and through all frequencies, so it's more or less white light. And so what we have is that the outer layers of a star and also the atmospheres of certain planets won't allow white light that is either being produced, in the case of a star, it's being produced by the star, or in the case of a planet being reflected by the planet. The outer layers of the atmosphere, the gas in the atmosphere, won't allow the white light to pass through, and it absorbs certain frequencies of light. And what this gives us is sort of the opposite of a line spectrum. What we have is an absorption spectrum. In the case of hydrogen, the absorption spectrum looks as follows. So it looks like a continuous spectrum with certain colors missing. And if I go up to my line spectrum, I see that the colors missing are the colors of the emission line spectrum for hydrogen. So what this means is that the composition of the planet or the star is mostly hydrogen. And so the hydrogen line spectrum is what's being absorbed by the gas when the light passes through it. And so what I have is dark lines instead of bright lines. So each dark line represents the specific frequency or wavelength absorbed by the gas. And these would be present in the line spectrum. So if I overlap what's missing, I find the line spectrum of the gas that I'm looking for. And that line spectrum in this case would be hydrogen. For different gases it would be different. But I can tell that this atmosphere or the outer layer of gas around the star is mostly hydrogen. So each dark line represents the specific frequency or specific wavelength. And again, that corresponds to the specific color. And so I can overlap the line spectrum and see which colors are missing, and I can tell hence what gas I'm observing. And so the absorption spectrum is sort of the inverse of the line spectrum. Now, why does this happen? And this happens because electron transitions will give off photons in all directions. Remember, I've drawn the photons moving in a very specific direction here, but in reality, the photons will be given off in all directions. So the white light sends out, the white light passing through the gas, only the specific frequencies are absorbed. And even though, so the white light will be moving towards our eyes, imagine it in this way, as the white light moves towards our eyes, the specific frequencies for hydrogen, in our case red, blue, purple, violet, are absorbed and then re-emitted in all directions. So what we get is, besides the white light, besides the continuous spectrum of all the visible colors in the white light, we have that the hydrogen spectrum being emitted in all directions has a lower intensity. Because unlike the white light that is all traveling towards our eyes, the line spectrum for the hydrogen is being emitted in all different directions. And so we notice a lower intensity, hence the dark lines. And so we can immediately tell that this is hydrogen. So let me just write this down. So the electron transition back to the ground state will emit photons, but emit the photons, red, blue, purple, etc., in all directions, not specifically towards our eyes. And that means that the intensity is lower, and hence we see them as dark lines rather than bright lines. And so this, like I said, reduces the intensity. And so we can see that the absorption spectrum is sort of the inverse of the line spectrum. And now we have a clearer idea of why the word quantum appears. We can see that the energies of photons are quantized, the energies of the electrons in atoms are quantized, and yes, everything on the small scale has to agree with this quantization. So the idea that energies can take a continuous range of values doesn't exist anymore. And so this is only the introduction to quantum mechanics, but it's a good introduction to understand the concepts and understand why our Newtonian mechanics and our classical physics doesn't work on all scales and all sizes. It has to be adapted for the small scale, which we call quantum mechanics. That's all from me, Mr. K, this time on Everything is Relative. Be sure to like and subscribe and follow me for more videos. See you next time.